now before we move on to a power series, let's examine a few effects of what it means to be, of what differentiability then implies. It's going to be insignificant. So first of all, in very simple words, what does it mean to be holomorphic at a point? It means that the total derivative exists in the Calc 3 sense, and that the total derivative is actually very special. Right? It's very special because instead of mapping a rectangle to a parallelogram, it in fact maps it to the same rectangle. It's a rectangle of the same shape. There are a few other things about it. So let's consider some examples and consequences of what holomorphic functions imply. So first example is if f of z is holomorphic, would f of z bar be holomorphic? What do you think? So what do we mean? So we're saying that f of z is equal to u of z plus I d of z. Right? That's what it means. And f bar of z is just u of z minus I d of z. It's the reflection of this vector through the x-axis. So here is what happens. I can show you by a picture. So suppose that this thing is, this vector is f of z. I just conveniently place it at the origin. I mean, usually it might be at some other point, doesn't matter, right? So this is the vector f of z. And I can extend this vector. And on top of that vector, I can decide to place the vector dz. So the vector dz makes some angle phi with this axis that I just drew. What is f going to do to this vector? So in other words, this is the point f of z. I want to examine what happens in the vicinity of f of z. What is f of z going to do to this vector? Rotate it and stretch it. So I'm going to rotate it by the angle theta. And I'll just assume it's counterclockwise. Right? So I'm going to rotate it by an angle theta and stretch it. So that is f applied to dz. This is the angle theta. Okay? Now, hopefully I'll draw it well enough. What's f of z bar? How do I draw f of z bar here? Exactly. Take this vector, reflect in the x-axis. So this vector is going to be here. That's f of z bar. this is this line that was rotated. And this is that original vector dz. So I can just take the same vector dz and place it in the same location. So this is the vector dz. So the z makes, again, some angle there. So what's going to happen? See, what's going to happen is that the image of this vector is going to be this vector, but now pointing like reflected. It's going to be this thing. Again, the stretch is the same. But what's the problem? The problem is that we would first have to rotate by this angle, which varies depending on where I place the z, and then by the angle minus theta. Right, so this we would have to rotate first to position this vector on this line, and then by minus theta. And depending on where this red vector is located, I will have to rotate more or less. So there is no uniform rotation that is happening. See? In this case, no rotation by the same angle. Yes?
Doesn't like to give the same symmetry just to be seen happens to be going into the orbit on the bottom?
No, I mean it's going to be the way you can picture it is that this would be here and so no, it's going to be by reflection. It's going to be going. I think.
Give the symmetry between F and F bar. The BC F bar is supposed to go into the
No, this is the same vector. So you just take the same vector and place it. It's not reflected. This vector is not reflected. That's the point, right? So how do you judge what the function is doing? You just see this vector, you can just reposition, right? You see what we're doing is we've just picked an arbitrary vector and we observe that it's always rotated by an angle theta counterclockwise. Now I pick the same vector, I place it here, and I observe that the rotation now is varying, right? So sometimes it's more, sometimes it's less. The farther this vector is away, the more I have to rotate, right? So this vector will always be rotated by the same amount. But this vector, if I just, but here, I will have to first rotate to bring into coincidence with this line, right? And how much do I have to rotate? If you want the precise formula, I mean, you see, this is the original line, right? This is the original line, right? So the amount of rotation here is what? So dz has to be rotated by what? By minus 2 phi minus theta. Right? Something like that. Or is it minus 2 phi? Or just check. But definitely minus 2 phi, because you see that we have to rotate first to bring it here and then again to the reflection, right? So this is definitely, and just to verify, it's 2 phi, something like that. So in essence, this tells you there is no uniform rotation. Yes.
So if you
keep the top red vector, right, as it is,
Mhm.
and see what the reflection is going to look like? What would be the reflection in that case?
Which vector? This?
So yeah, let's leave that, right? And we don't draw any vector down there, right? What would be our reflection?
Of this vector?
Yeah.
It's going to be this, just flip it over.
Right. So then, are we not going to follow the same principle that we did with the other vectors? Why we are manually basically tweaking the vector at the bottom?
I mean, I just want to. This is just for assistance in trying to verify what happens to the conjugate function. So the conjugate function.
So what we can do, even if it flips down, right, and you bring back to the same position, just like at above, you're saying that you're not going to get the same answer.
No, if it's flipped down, you are going to rotate it by minus theta. That's okay. But here's the subtlety, right? You are examining, say, this vector. You just now want to see what would happen to this vector under this image. So if I take the same vector, place it here, and I see that that depending on what angle this vector makes with this red axis, its rotation is going to change. The angle of rotation will change. That's the point. But the angle of rotation is not supposed to change. That's the problem, right? So the conclusion from this. The conclusion is that f of z and f of z bar are both holomorphic. If f of z is constant. So if it's constant, then in fact the rotation is zero. It just crushes the vector to zero. That's the only way it can be holomorphic. So I hope I didn't botch it. Do you understand my point here? It's a little subtle. So what I'm examining here is f of z is assumed to be holomorphic. So pick any vector in any position. This z is supposed to represent a fixed vector. What's going to happen to it? It's going to be amplified and rotated. Amplification is preserved. It's going to have the same amplification. Just look at the reflection, right? It's going to be stretched in both cases by exactly the same amount. But what's going to be the problem? The problem is that depending on the angle that this vector is making. So for example, if I select z to be this vector, the rotation is going to be just simply minus theta. Or actually, minus 2 theta. I mean, that's one thing. I think I have minus 2 theta or theta. Forgive me for being clumsy with this, right? But basically, if it's this vector, there's going to be one sort of rotation. If it's another vector, the amount of rotation changes. That's the point of what I'm trying to say. Okay? Could be minus 2 theta, just somehow. Yeah, but another thing to say about this is that if f of z is conformal or is holomorphic, then we know that this is the picture. So if I take dx and I take dy and I apply f to it, and suppose that I got this to be my, roughly speaking, f applied to dx. What's going to be, where am I going to find f applied to dy? 90 degrees where? Counterclockwise. That's because you see each vector was rotated. So this tells you the rotation. It tells you that the rotation was some angle theta from the x-axis, so the other vector will also be rotated by the same amount. So this vector is going to be I times f of dx, which is going to be equal to f applied to dy. Approximately, by the way, this is approximation, right? Approximately. So the angle is going to be traced in exactly the same form. Now suppose that I apply f bar here. If I apply a bar, let's say if we try to keep true to that picture, so dx was mapped to here. Where do you expect f of dy to be mapped? Yeah, very good.
Clockwise?
It's going to be rotate, but clockwise. Do you see that, guys? So it's going to be rotated. So you see the angle here is traced this way. Now the angle is traced this way. So this would be f applied to dy, which then is equal to minus I f applied to dx. So this is called anti-conformal because you see the size of the angle is preserved, but the orientation of the angle is not preserved. The sense of the angle is not preserved. So this is called anti-conformal.
What is called anti-conformal?
Because so that means by definition.
Why is called anti-conformal?
Conformal means preserves the size of the angle and the sense of the angle. Anti-conformal, I guess, exactly. It doesn't seem like fully against it, right? But
what do you call anti-conformal? F bar or F?
F bar would be called. F bar. You're right. Sorry. F bar is anti-conformal because what you mean by that is it preserves the size of the angle. But not its sense. In other words, it reverses the direction the angle goes. So that's anti-conformal. So in other words, you can have another Cauchy-Riemann equation. So the Cauchy-Riemann equations in that case will be, or anti-conformal Cauchy-Riemann equations. Will be, if I just take f of x, f bar of x, I'm sorry, right? And I multiply it by minus I. Multiplied by minus I means rotate 90 degrees clockwise, right? And that will be what? That will be f bar sub y. That's exactly what's happening. So in other words, the point of this approach, it's a nice approach because you kind of see why Cauchy-Riemann equations hold. What's happening there. In your homework assignment, there is a polar version of Cauchy-Riemann, right? So see if you can come up with a good explanation.
So I have a question. So F bar is always anti-conformal.
If F is holomorphic, then F bar is going to be anti-conformal, right? So in other words, if we know that F is differentiable in the complex sense and its derivative is not equal to 0, I mean, derivative equals 0 is the trivial case of where you are crashing to 0, right? But aside from f prime equal to 0, shape is preserved, right? So if f is holomorphic and its derivative is not 0, then f bar is not going to be holomorphic. You cannot differentiate it in the complex sense, and it's anti-conformal. So in other words, the angles are preserved, but they are just reversed in direction.
But you said the size of angle is preserved, right?
The size of angle is preserved.
Yeah, and their EZ has to be rotated by minus 2t minus theta.
This, just again, I mean, I'm in a little bit of a stupor. I'm not sure if the minus theta is true. I think I see that the minus 2phi is true, right? But the point is, again, is that the amount of rotation of a fixed dz is going to vary depending on the angle of dz. That's the point. Okay, you can just play around with it and verify it. Again, it's a little bit like being in deer in the headlight, right? I mean, you're staring, but you have very smart faces, and I'm very afraid. I'm intimidated. Right?
My question is, are those two not violating each other?
You mean that dz is not being rotated by a uniform amount, and this thing?
Yeah.
Apparently no.
So in the first case, the size of the angle is not preserved, I guess, right?
The amount of rotation is not preserved. Not the size of angle. here is how I reset this. Okay, let me just try to show it. There is no confusion. So again, what we have is we have a small square. Okay? And then I apply f to that square. If I apply f to that square, again, the way you think of it is the square is microscopic, so you can think that f can be approximated by a linear map. Right? So this point here is z, and now the new point is going to be f of z. And assuming that discussion that we had for the differentiability of f, and we're assuming it's differentiable, we know that each of those things are going to be rotated. Right? Let's in this case draw the rotation to be clockwise. So let's say instead of going counterclockwise, in this case the rotation is like this. So this is where this is dx, and this is the image of dx. This is almost the image of dx. Here you approximate it by differential, right? So if this is f of dx, where do you expect to see this? It's all, you see, what it suggests is that all the vectors were rotated by some angle theta. So dy will be mapped here. You prefer that indicated with the eye, so there is a vector. So you can see that here the angle went this way. Here it's again 90 degrees and goes the same way. Now, what does it mean that I apply f conjugate? Applying f conjugate means that I get this picture and then I reflect it in the x-axis.
Okay.
You see what I'm saying, right? So that's how I know that the angle is preserved. So then, really, if I want to consider what is the image of this thing under f conjugate, it's really the same as taking this picture and applying, and this is just the map z into z bar. In other words, it's enough to analyze just this function. Right? And then what's going to be the image of this thing? The reflection of it in the x-axis is going to have, it's going to reverse orientation. So it's like taking the page and flipping it. Right?
Yeah, I got it.
Okay, so we have something like this, and something like that. And now the sense of the angle is reversed. But again, you see, so the sense of the angle is reversed. So even by just knowing this picture, you know it cannot be conformal because conformal just rotates the vectors. But it cannot be that they are reversed, right? Rotation never reverses the sense of an angle. So already by this picture, you know it's impossible for the conjugate to be conformal without doing extra analysis. But then you ask yourself, what's happening? The angle is preserved. It's very subtle. So then you realize that what's happening is, although it seems it's not easy to see, but actually the different disease, in order to achieve this picture, have to be rotated by a different amount. If you just want to achieve this picture by pure rotation, right? If you achieve it by rotation and reflection, then you don't need to do it. But if you want to achieve it by pure rotation, you have to do it. Make sense? Just a second. You.
For the NP follow case, right? You said we're going to have another Cauchy-Riemann equation.
I mean, you don't have to worry about it. I'm just saying that this equation has to be satisfied. It has to be satisfied.
Will that satisfy?
If f is holomorphic, if we have that f is holomorphic, then this equation should be satisfied.
But I'm saying f prime, for example, f bar, for example, is not holomorphic, right?
No, it's not.
Right. So then there won't be any Cauchy-Riemann.
No, all I'm saying is I'm just relating the partial derivative with respect to x, to the partial derivative with respect to y. All right? Yep.
Sense just means orientation for angles, like it's like saying.
Sense is basically if the angle, in order to go from one ray to another ray, I rotate counterclockwise, then that has to be preserved. I have to continue rotating counterclockwise. Okay?
The only
That's what
problem
sense.
here is the sense. That's the only thing that makes it not conformal.
Say it again? Yes, the sense, right?
Okay.
The sense of the angle must be preserved. In other words, if you consider geometry, right? You can take this piece of paper. That's one version of isometry. You just take it and you rotate, right? The other version is doing this, flipping over.
So for all things that are nice, this is still, that's why they're giving it a name after it's
Yes,
still nice.
it's very nice. We're going to actually study those things very soon.
Okay.
So again, guys, I'm hoping that this is new to you. It's definitely important when we talk about Mobius transformation. I'm going to give you a set. I'm going to give you another example so you have a feel for it. Yes?
Yes, I'm sorry. Can you repeat one more time conformal and
Okay,
the sense-
conformal means that the direction of the angle is preserved and the magnitude of the angle is preserved. Anticonformal means only the magnitude of the angle is preserved, but the sense is reversed. That's the anti part, right? Anti means that the sense is reversed. It's like this, right? So, how does it work from your perspective? So, I need to rotate this arm. I'm bad at it. Counterclockwise, I guess, right? Or clockwise, right? I'm bad at left and right.
Counterclockwise.
Okay, right? So that's why I have problems, right? So you have to rotate this way, right?
Right.
I need to actually think about when people tell me drive, right? They tell me turn left. I then have to think, where is left? Left is where my heart is, right? So, do I have a heart? That's the next question. So, yeah. So anyhow, you see, look at it. You need to rotate this here, but if I reverse it, right, I need to rotate it by a different angle. If I rotate it in the same sense, right? I mean, so here, right? I need to rotate by 90 degrees counterclockwise, but if I take just flip it over, I will need to rotate. If I want to still use counterclockwise rotation, I will have to rotate by 3 times 90 degrees. You see what I'm saying? So that's very subtle, but that's why the amount of rotation is different when you reflect.
Thanks.
Yeah. Okay. Cool. So. All right, so here is another visual question. So, suppose that I'm in the plane and I have a holomorphic map, and in a region where it's holomorphic, I trace the outline, and I send a particle moving along this outline. Okay, so the position of this particle is z of t. Okay, so it's just moving around this path in the way I've drawn. So that's going to be important when we talk about Mobius transformation. So let's suppose that we want to examine this region. We know we will look at this paddle. And then I apply F holomorphic. Well, holomorphic with possible exception, there is a hole here, right? There is a hole somewhere inside. So that would be achieved. So that is holomorphic, and now I get the following picture. So, if this is d of t, this point is the image f of z of t. Okay? And what I observe is that when I map this image, I observe that this puddle that used to be on the inside is now on the outside. Yeah? So the question is, where does the particle move? So here it was moving here. How is this particle going to move along this curve? Very good. In the opposite direction. You see, it's going to move here is y. So you have this. You can just the arrow, the x indicates the direction of motion, right? And then we have another pointing into the follow, right? So now, wherever this arrow is, when I rotate it by 90 degrees counterclockwise, it has to be pointing into the puddle, right? So the only possibility of that, if I rotate 90 degrees counterclockwise, is that my arrow is pointing here. Because the other arrow must be pointing to the puddle. I need to be rotating by the same amount of angle. Okay? So the motion is in the opposite direction. If this region was mapped to the inside, that would be rotating in the same direction. So, one other consequence of what holomorphic functions do is the following. So you can say that holomorphic functions are rigid. I'm going to explain that better when we get to chapter 2. So what do I mean by rigid? So if I'm going to take and draw an infinitesimal rectangle. So this is an infinitesimal rectangle, and I apply f. The shape is going to be, if it's very small, it's going to be another infinitesimal rectangle with the same dimension, the same proportionality preserved. What would happen to the other rectangles? So you see it's like a mosaic. So the next rectangle, we cannot stretch this line, so it's going to be another rectangle placed here, another rectangle placed here. So in essence, once you see a small shape, it's like building a mosaic. Right? It's like you take this mosaic and you just place it around. It tells you exactly how to place it. Well, I mean, it's not obvious that it tells you exactly how to place it because there is error, right? It's not truly going to be a perfect rectangle. Otherwise, it would be pretty boring. And all holomorphic maps would just create the rotation, right? The translation. But you can see that it's definitely more rigid than this for mosaic correctly? Sure? Like a mosaic. This is when f is holomorphic. But if I were to apply g, then we're just some regular differentiable function. What is the picture that I will get? Well, it's going to be some parallelogram here, and then here it could be some other parallelogram. See, just knowing this parallelogram doesn't tell you much about the next one because, well, the next one will be possibly twisted like that. No, there's more variation. I don't preserve the angle, so more variation. So let's give a more concrete example of the sense in which it's rigid. Find all homomorphic maps F from C to C that map parallel lines to parallel lines. So what's happening here, it's going to map parallel lines to parallel lines, which means that if I take horizontal lines, well, these horizontal lines will be mapped to some slant lines. I don't know where they will go. They will stay parallel. Okay? So let's suppose that this angle is theta. If this angle is theta, then what I can do is I can select capital F of Z and define it to be e to the minus I theta little f of z. And what this accomplishes is that I can now assume that the parallel horizontal lines are mapped to another set of parallel horizontal lines. Do you see that? So this new function is also holomorphic. Because it's just a multiplication by a constant. And f of z maps horizontal lines to horizontal lines.
Wait, so if you compose those two functions, so you get the identity.
The identity, no, not necessarily. Because I am not saying that they are in the same position. But almost. You're right, almost, right? And I'm not saying that the spacing is preserved, right? All I'm saying is that, so for example, this could be distance d, and this could be some k times d. And they don't have to be on the same level. Okay? So, but all I know is that f of z is holomorphic, and f of z maps horizontal lines to horizontal lines. Where does it map the vertical lines? To vertical lines. How do we know that? Again, just to make sure that it's rigorous. Well, we claim that it's mapping parallel lines to parallel lines. So the vertical lines will have to be mapped to some set of lines. But vertical lines are perpendicular. And holomorphic maps preserve the angle. So there is no other choice. So what does it mean? So I can write f equal to u plus ip. And in terms of the Cauchy-Riemann equations, I can take the partial derivative with respect to x, right? So I can take f sub x, and what is that going to equal to? ux plus I dx, and what's that equal to? What's dx equal to? If I'm mapping horizontal lines to horizontal lines, what's dx equal to? 0. Excellent, right? Because there is no change in the y coordinate, so it's 0. So the solution here is that this is just simply ux. And what we have also is that the partial derivative with respect to y is going to be so it's going to be u sub y plus I d sub y, which is equal to I dy, right? There must be, right? And what does this imply? It implies that if I rotate this vector by I will get that vector. So if I take I times fx, I will get fy. That's because I'm assuming it's holomorphic. That's what I did, right? So that implies that ux is equal to vy. And we also have the ordinary Cauchy-Riemann equations. We have that, so we also, by the way, have that vx is equal to 0. And we have that uy is equal to 0. Right? So that implies that u is equal to, so when you take the derivative with respect to y at 0, it must be just a function of x alone. So u is equal to some h of x, only dependent on x. And v only dependent on y. Right? And by using the first equation, we also have that ux is equal to h prime of x, which is equal to d of y, which is equal to k prime of y. In other words, you just have that so you have that h prime of x is equal to k prime of y, which implies that h prime, which implies that h of x and which implies that h prime of x is equal to k prime of y, which is equal to some constant. You agree? So because they don't you just fix an x and change the y, so you know that k prime of y is constant. And now do the opposite. Fix y and vary the x, so that tells you that h is constant. So you get a, and that implies that h of x is ax, and k of y, ax plus, let's call b1, and k of y is ay plus b2, for some constants, b1 and b2. So that implies that u is equal to h of x, in other words, it's equal to ax plus b1, and v is equal to ay plus b2. And then we have that f, which is equal to u plus iv, will then be equal to a c, because that will be x plus iy, plus b1 plus ib2, which is just some constant b. So that's linear. Okay? So if this is linear, all I need to do to obtain f, you can just say that f of z is equal to ei theta times, in this case a is real, by the way. You notice that in this case a is real. So in general, f of z is ei theta multiplied by f of z, which will be some cz plus d, where now c and d are just any complex numbers. Okay? So we just that's an example. There are many examples. There are some more sophisticated examples using polar coordinates, but we'll deal with them later. All right. So let's talk about power series. So we are gonna later very rigorously prove that holomorphic function is determined by a very tiny set of points. As soon as you know them, you know everything about this function. Please continue. So we are going to consider f of z equal to the summation n equal to 0 to infinity a sub n z to the n. Now what is power series? If you just look at it in expanded form, a0 plus a1z plus a2z squared plus onwards, right? So this is like an infinite polynomial. Remember in the first lecture we mentioned that you started studying complex variables from looking at the roots of a polynomial, right? So in essence, complex variables will continue that tradition. So series is absolutely convergent. It absolutely converges if taking absolute value of all the terms will reduce a number that is less than infinity. In this case, it's a real number, since we're taking one. So here is the first proposition. So suppose f of z converges. Mind you, not absolutely, just converges at c equal to c0. In other words, suppose that I find that this thing gives you a complex number if I plug in z0 without taking any absolute value, right? Then f of z is absolutely convergent for all numbers whose modulus is smaller than the modulus of 0. Okay? Proof. Converges. That implies that the sequence n a sub n, z sub 0 to the n, goes to 0. You agree? That implies that a sub n z 0 to the n is quotient. So So it's clustering at 0, in particular it's Cauchy. And that implies that if I take the modulus, then this modulus for all n is going to be smaller than some number b. Bounded. You know what I'm saying? In other words, all Cauchy sequences are bounded. So I can select some big enough number that is bigger than the modulus of all of them. Now we have pretty much all we need. So then if I consider the series n equals 0 to infinity a sub n c to the n, this is the same thing as n equals 0 to infinity a sub n c0 to the n times z over z0 to the n. Now this implies that n equals 0 to infinity absolute value a n times absolute value z to the n is going to be less than or equal to n equals 0 infinity a n z0 to the n z over z0 to the n, and that itself is less than or equal to n equals 0 to infinity b times r to the n, where r is equal to z over z0, which is smaller than 1. So that is convergent, absolute convergent. Okay? So this is actually pretty interesting because what is this saying? This is saying that if I have a point z0 at which I know convergence occurs, then anywhere inside of the circle whose radius is z0, anywhere on the inside, I have absolute convergence. Right? If I converge at this point, everywhere on the inside I have absolute convergence. So let's just think about it for a moment. What does it say? If I found a point z0 at which my power series does not converge absolutely, can the radius be extended beyond that point? In other words, imagine I found, instead of this theorem saying that it converges absolutely at z0, I found that at z0 it does not converge absolutely. Can this disk expand further? No, right? Because if it expanded further, that would imply that z0 will be in the region where absolute convergence happens. So this is actually going to be important when we study those functions, right? You can expand. So this is going to turn out to be a holomorphic function. We really only saw very few versions of those. We saw polynomials, and that's pretty much it. We haven't seen any holomorphic function yet that is not a polynomial. And in fact, we would not see any. I mean, some of them we cannot globally polynomials, but all of them will prove to be locally polynomials. Okay? So they behave very much like that. So that will tell you that that a holomorphic function cannot extend once you have a singularity of sorts. Right? If you have some singularity on the boundary, it cannot be extended uniformly through that singularity. So there are going to be examples of holomorphic maps that cannot be continued beyond the circle. That would be in chapter 2 of Stein. Okay? How much more time do we have?
1 or 2.
1 or 2 minutes. Do you know the root test? Can I just state it and you look at the proof? Right? You know the root test, right? If you don't, just stop. So root test. And that tells you that given there exists some r that is less than or equal to infinity, bigger than or equal to 0, such that if Z is contained in a circle of radius r, series converges absolutely. So, if Z is bigger than r, series diverges. And R is given by the following formula. One over R equal to limit supremum of the absolute value a n to the 1 over n. And you would say that 1 over 0 is equal to infinity, and you would say that 1 over infinity is 0. This conversion, right? So, okay, good. So this proof is in Stein. You can look at that in Stein or construct your own proof.